8 of solid state. Dear students, this video is based on the new syllabus 2021. In this video, you are going to see and understand close packing in 1 dimension, 2 dimension and 3 dimensions. In addition to this, we are going to understand tetrahedral voids and octahedral voids and packing efficiency in simple cube, body-centered cube and face-centered cube and the unit cells. But before starting with that, like the channel, share it with your friends and subscribe it now. Let's get started with the video. Packing of particles in crystal lattice. Constituent particles of a crystalline solid are close packed. While describing the packing of particles in a crystal, the individual particles are treated as hard spheres, as it can be seen here. The closeness of the particle maximizes the interparticle attraction. The number of neighboring spheres that touches any given sphere is its coordination number. Magnitude of the coordination number is the measure of compactness of the sphere in closed packed structures. The figure here you can find 3 figures A, B, C. These are showing the close packing of spheres in different ways. The number of nearest neighbors of a particle is called its coordination number. Magnitude of the coordination number is a measure of the compactness of the sphere in a closed packed structure, as you can see here. Here the coordination number is different. In this figure, the coordination number is different, whereas in this close packing of sphere, the coordination number is different. Thus, in close packed arrangement, the coordination number depends on the number of nearest neighboring spheres. We are going to study this packing in detail in further slides. The 3-dimensional modes of packing can be easily understood by dividing the whole process into 3 steps. Close packing of spheres in 1 dimension. In that 1-dimension close packing, there is just one way of arranging the spheres. Here, the spheres are arranged in a row, touching one another. As a result, each sphere is in contact with 2 neighboring spheres. Thus, in 1-dimensional close packing, the coordination number is 2. Close packing of spheres in 2 dimension. Close packing structures in 2 dimension can be generated by stacking rows of 1-dimensionally close packed spheres one above the other. They can be done in 2 ways: square close packing and hexagonal close packing. Square close packing. In this type of packing, the second row of the spheres is placed in contact with the first row in such a way that the spheres of the second row are placed exactly above the spheres of the first row. In such an arrangement, the spheres are aligned horizontally and vertically such that each sphere is in contact with 4 other spheres. So, coordination number is 4. If we call the first row as A type, then the second row being same exactly, so it is also called A type. If we keep on placing such similar rows one above the other, then such an arrangement is known as AAA type of arrangement or square packing. Hexagonal close packing. In this type of packing of spheres, the second row of the spheres is placed in the staggered manner such that the spheres fit in the depression of the first row. If we call the first row as A type, then as the second row is different from the first row, it can be called as B type. Now, if we place a third row above the second row in the similar manner, we will observe that the third row spheres are aligned with those of the first layer, and each sphere is in contact with 6 other spheres. So, the coordination number is 6. Similarly, on placing the fourth layer, we will observe the fourth row of the sphere are aligned with those spheres of the second layer. Such type of arrangement is known as AB type of arrangement or hexagonal close packing. If we compare square close packing and hexagonal close packing, we observe that the empty spaces are less in hexagonal close packing than compared to square close packing. Now, what are these empty spaces and what role do they play in the packing efficiency? The empty spaces in between the spheres are known as voids. These voids are responsible for decrease in packing efficiency of the solid crystal. More the number of voids, less is the packing efficiency of the crystal. Now, you must be wondering what is meant by packing efficiency. We have discussed about this in the later part of the section. Now let us study about the close packing in 3 dimensions. 3-dimensional close packing from 2-dimensional square closed packed layer. This type of packing is obtained by placing 2-dimensional square closed packed layer above the first one, such that the spheres of the second layer are exactly above the spheres of the first layer. In this arrangement, the spheres of both the layers are perfectly aligned horizontally and vertically. On arranging layers one after the other in this pattern, we will observe that each sphere is in contact with 6 other spheres. 4 from the same layer, 1 from the layer above and 1 from the layer below. So, the coordination number is 6. If we call the first layer as A type, and since all the layers are also of same type, this kind of arrangement is known as AAA type of arrangement. On observing carefully, we will find that this arrangement has generated a simple cubic lattice, and its unit cell is primitive cubic unit cell. Dimensional close packing from 2-dimensional hexagonal closed packed layers. The 3-dimensional hexagonal closed packed structures can be obtained by placing 2-dimensional hexagonal structures one layer above the other. Placing second layer over the first layer. Let us take a 2-dimensional hexagonal closed packed layer A. Notice that this layer has a triangular voids. Place the similar closed packed layer in such a way that the spheres of the second layer are placed in the depressions of the first layer. As the spheres of the second layer are aligned differently as compared to the first layer, so let us call this layer as B type. On observing, we will notice that not all the triangular voids of the first layer are covered by the spheres of the second layer. This gives rise to a different arrangement and the different voids. Voids. There are two types of voids. Tetrahedron voids denoted by T, octahedron voids denoted by O. Let us study how these voids are formed. When we place a closed packed layer above the depressions of the first layer, we will notice that at some places the triangular voids of the first layer are being covered by the spheres of the second layer. At such places, a type of void is formed. This type of void is known as tetrahedral void, T. Since a tetrahedron is formed by joining the centers of the four surrounding spheres, while at other places we will notice the triangular voids of the first layer coincides with the triangular voids of the second layer, such that their triangular shapes do not overlap. At such places, another type of void is formed. This type of void is known as octahedral void, O. Since an octahedron is formed by joining the centers of the six surrounding spheres, now, in case we need to calculate the number of tetrahedral and octahedral voids in a crystal structure, then just knowing the number of spheres, we will serve the purpose. For suppose there are n spheres in the crystal structure, then the number of octahedral voids generated is equal to n. The number of tetrahedral voids generated is equal to 2n. Placing third layer over second layer. Now let us place third layer over second layer. Stacking of third layer over second layer can be done in two ways. First, by covering tetrahedral voids. Second, by covering octahedral voids. By covering tetrahedral voids. The tetrahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer will get exactly aligned with the spheres of the first layer. So, if we call this first layer as A type and the second layer as B type, then the third layer will also be A type. As a pattern of spheres is repeated alternately, so this pattern is known as AB pattern, and the structure formed is known as hexagonal close packed HCP structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer and 3 from the top layer. So the coordination number is 12. Covering octahedral voids. The octahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer are not aligned with the spheres of the either first layer or the second layer. So, if we call the first layer as A type and the second layer as B type, then the third layer will be of C type. Now, if we place the fourth layer over the octahedral voids of the third layer, then the sphere is aligned with the spheres of the first layer. Thus, this pattern is known as ABC type pattern, and the structure formed is known as cubic closed pack CCP or face-centered cubic FCC structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So, coordination number is 12. Number of voids per atom in hexagonal closed packing and cubic closed packing. Let us now understand the number of tetrahedral voids and octahedral voids in this arrangement. In a closed pack structure, whether the CCP or HCP, if there are n spheres, number of spheres in the packing, then the number of octahedral voids is equal to the number of spheres, while the number of tetrahedral voids is equal to 2n. For example, in a CCP arrangement, if 4 atoms or ions are present per unit cell, then the number of octahedral voids is also 4, while the number of tetrahedral voids is 8. Packing efficiency in crystals. Packing efficiency in crystals. The particles such as atoms, ions, or molecules in crystals can be packed together in several different ways. In each type of packing, there is always some vacant space in between the constituent particles in the form of voids. We know there are 2 types of voids in a packing: tetrahedral voids and octahedral voids. Thus, in a packing, only a part of the total available space is occupied by a constituent particle. The percentage of the total space filled by the particles is called packing efficiency. Different types of packing arrangement have different packing efficiency. Now, let us calculate the packing efficiency in different packing arrangement. Packing efficiency of metal crystal in simple cubic lattice. In simple cubic unit cell, the 8 atoms or particles or spheres occupy the corner position. Therefore, the particles are in contact with one another along the edge. The number of atoms per unit cell in a simple cube is only 1. Each atom is considered as one sphere. Volume of one atom or one sphere is equal to 4/3 pi r cube. Let A be the edge length of the unit cell and r be the radius of the sphere. The spheres at the corners are touching each other. Then we have the edge length A is equal to 2r. the volume of the cubic unit cell is equal to A cube, which is equal to 2R whole cube, which is equal to 8R cube. Percentage efficiency or packing efficiency is equal to volume of one atom divided by volume of cubic unit cell into 100%. Packing efficiency is equal to 4 by 3 pi r cube divided by 8r cube into 100, which is equal to pi by 6 into 100. Packing efficiency is equal to 52.36%, which is equal to 52.4%. The vacant space available in the simple cube is equal to 100 minus 52.4%, which is equal to 47.6%. Packing efficiency of metal crystal in body-centered cubic lattice. In a body-centered cubic structure, there is a particle at the center of the unit cell, in addition to the particles at the corners. Thus, in a body-centered cubic structure, there are three spheres in contact with each other along the body diagonal. Let A be the edge length of the cube and R be the radius of the sphere. The body diagonal AF is equal to C and the face diagonal FD is equal to B. Then AF is equal to C, which is equal to 4R. Now let us calculate the body diagonal C and face diagonal B using these values. We can calculate A. Let us consider the triangle EFD. By using Pythagoras theorem, we have FD square is equal to EF square plus ED square. B square is equal to A square plus A square. B square is equal to 2A square. Therefore, B is equal to square root of 2A. Now, in triangle AFD, AF square is equal to AD square plus FD square. C square is equal to A square plus B square. C square is equal to A square plus 2A square, which is equal to 3A square. C equal to square root of 3A. But C is a body diagonal, which is equal to 4R. Therefore, C is equal to square root 3A, which is equal to 4R. A is equal to 4R by square root of 3. Volume of the unit cell is equal to A cube, which is equal to 4R by square root of 3 raised to whole cube. In body-centered cubic unit cell, the number of particles per unit cell is 2 atoms. Each atom is considered as one sphere. The volume of the 2 atoms is equal to 2 multiplied by 4 by 3 pi r cube, which is equal to 8 by 3 pi r cube. Packing efficiency is equal to volume occupied by 2 spheres in the unit cell into 100 by total volume of the unit cell percentage, which is equal to 8 by 3 pi r cube into 100 by 64 by 3 square root of 3 r cube percentage, which is equal to 68%. Packing efficiency is equal to 68%. In body-centered cubic unit cell, 68% of unit cell is occupied by atoms and the rest 32% is plain empty space. Packing efficiency of metal crystal in face-centered cubic lattice, CCP or HCP lattice. Face-centered cubic unit cell. Let us calculate the efficiency of packing in CCP structure. Cubic close packing is same as cubic packing. In this type of arrangement, the particles are touching one another along the face diagonally. Let the edge length of the unit cell be A, the radius of the insphere be R, and the face diagonal be B. AC is equal to B, which is equal to 4R. Now, let us calculate the edge length A by applying Pythagoras theorem. In triangle ABC, AC square is equal to BC square plus AB square. B square is equal to A square plus A square. B square is equal to twice A square. Therefore, B is equal to square root of 2A is equal to 4R. Therefore, A is equal to 4R by square root of 2, which is equal to 2 square root 2R. Volume of the cubic unit cell is equal to A cube, which is equal to 2 square root 2R whole cube. We know that each unit cell in face-centered unit cell or CCP structure are 4 spheres or atoms. Volume of the 4 spheres is equal to 4 into 4 by 3 pi r cube, which is equal to 16 by 3 pi r cube. Now let us calculate packing efficiency. Packing efficiency is equal to volume occupied by 4 spheres in the unit cell into 100 by total volume of the unit cell in percentage. Packing efficiency is equal to 16 by 3 pi r cube into 100 by 2 root square root of 2r whole cube percentage. Packing efficiency is equal to 16 by 3 pi r cube into 100 by 16 square root of 2r cube, which is equal to 74%. HCP or CCP has a packing efficiency of 74%. Efficiency of packing in talk about the packing efficiency completely on one slide. You will understand and it's easy to remember. Packing efficiency in simple cubic, body-centered cubic, face-centered cubic or cubic closed packing and hexagonal closed packing. Each of them we are going to see. So these are already you have seen these structures, so you may remember the things very well now. So this is simple cubic closed packing. This is body-centered cubic closed packing. This is face-centered cubic closed packing, and this is hexagonal closed packing. So packing efficiency, as you have already learned, for simple cubic it is 52.4%, whereas in body-centered cubic it is 68%, in face-centered cubic it is 74%, and in hexagonal close packing it is again 74%. So on one page, if you remember the things well from these pictures as well as structures of these unit cells, you can remember it very well. Here you find a table. In this table, you will find the coordination number and the packing efficiency in the respective lattice. The first point shows simple cubic lattice. Here, the coordination number of simple cubic lattice is 6, wherein you will find one atom or one particle is surrounded by 6 particles. 4 particles in its own layer, 1 particle is above and 1 directly below. Let's see to it. Here you can see this is the center particle. In its own layer you will find 4 particles, 1 is above and 1 is below. In the second one, that is body-centered cubic lattice, the coordination number of atom is 4, wherein 4 particles are above the layer and 4 particles below the layer. Let's see how it is seen. So this dark blue colored central particle is surrounded by 8 particles. 4 particles in the above layer and 4 particles in the below layer. In FCC, that is face-centered cubic lattice, or cubic closed packing, or hexagonal closed packing, the coordination number is found to be 12. 6 in its own layer, 3 above and 3 below. Here you can see the yellow colored particle is surrounded here in its own layer by 6 particles, 3 above and 3 below. This condition is in HCP, that is hexagonal closed packing, and this you can see it in cubic closed packing. In this table, you will find here are some parameters for cubic system are given in relation to the edge length and the particles, which will be helpful for you for solving the numericals. Here the unit cells are given, which we have already learned: simple cubic, body-centered cubic, face-centered and close-centered cubic closed packing. Relation between A and R, where R is the edge length and A is the edge length and R is the radius. Here you can find the relation between the volume of one particle and here the total volume occupied by the particle in unit cell. Subscribe my channel, don't forget to like it and share it with your friends.